Hi, it's time for another math easy solution. Time to discuss further into applications of integrals and look at hydrostatic pressure and force, and now look at example 1 of this quick example series. It's pretty useful, basically applying integrals to physics and engineering. And so make sure to watch my last video on introduction to application of integrals and hydrostatic pressure and force, which I went over and introduced what they were in somewhat detail. So make sure to check those out. Basically, the example I'm going to cover is this one here. States a dam has a shape of the trapezoid shown in the figure below. The height is 20 meters and the width is 50 meters at the top and 30 meters at the bottom. Find the force on the dam due to hydrostatic pressure if the water level is 4 meters from the top of the dam. So if you look at the side view here, this is the dam right here, this is the side view. So just to illustrate it, well, what I mean is, so you have a dam like this, let's assume it's just a random vertical concrete dam like this. This is just simplified. So we have water on this side, so what we're going to end up having is actually a force being applied to it based on this, so this force can be applied to it based on the water pressure, because this is a weight of water here applying to it. And then if you look at the cross section, it looks like this, a trapezoid. So the water level is 4 meters from the top, it's 20 meters in height. Draw this all the way across here, you have 50 meters width from the top, 30 meters at the bottom, and then this here, let's just assume that it's perfectly symmetric. So this would be, so if we draw a triangle like this length here is 10, assuming it's perfectly symmetric. It doesn't state it here, but it actually is. So it's perfectly symmetric like that. So this is 10 meters, 10 adds up to 50. And this is like that. And now right here, this is the cross-section view. Cross-section view. So now in determining this force, the solution we're going to look at is basically we're going to take a thin slice across here and then find the force due to that thin slice of water, and then basically sum it up to infinity, and then we get an integral. Basically simple, the basics of integration, which I've done on areas, surface areas, etc. It's always going to be the same thing. So we just take small section, sum it to infinity. So in this case, we'll choose a vertical axis with origin at the surface of water, and that's because the water pressure increases with depth, as I showed in my last video. So we just need to deal with the origin like at the surface level, and we'll make it easier right here, as in the figure below, and I'll draw that out right now. Yeah, so what we will do is, let's just draw this shape again. So we have this. I'll draw this a bit more accurate. So it looks something like this. And now the water level is across here at 4 meters depth. And I'll draw the origin of the axis right across here. I'll draw this like this, going all the way down. So this is our x-axis. And the origin is 0 right here. Now we have it like this. This will make more sense as I get through it. So if this is 0 at this origin, is the water level at this point right here, this is going to be, well, -4 meters. So this is in meters. So we're just dealing with SI units, or meters. And then at this very bottom here, this is, well, 20 minus 4, that's just 16. So that's positive 16, that's -4. So we have positive going downwards. And now what we're going to do is, well, the depth of water is 60 meters, so we divide the interval from 0 to 16 into subintervals of equal length. We'll call this delta x, with endpoints xi, and we choose xi star to be just any or element of any number inside this interval from xi minus 1 to xi. And what this means, as I've gone over in my earlier videos on integration and proving proving integrals, this xi is, let's say, 1, 2, 3, or 4, 5, 6, etc. It just keeps going on. So if we take a thin slice, let's just cut a slice like here. Actually, Yeah, I'll draw this in red actually. So if I draw this, let's say, so this is any number inside here. That's all this means. So let's say we have this xi star, and then we take a thin slice across here. Actually, this point is the one that's at this point here. What I'm going to do is draw a thin rectangle. So at this point, I'm going to draw this like that. So this length across delta x. So in this point right here is our xi, and then here is our xi minus 1. So this xi star, it could be any x value inside of this small interval here. The reason we have it any value is because once we find a limit and make this delta x infinitely small, this xi star is going to be equal to xi or xi minus 1 because it's super small. And now the next step is basically to find the force due to this thin slice on the dam, and then we obviously sum it up to infinity and get an integral for that. So basically the ith horizontal strip of the dam, as I showed here, is approximated by a rectangle with height delta x like that, and width wi, so I'll draw that width is across like that, whoops, like this. So this width is wi, where from similar triangles we obtain the following. So what we get from similar triangles here is if we draw a line like this all the way from this very point. And the reason we're doing this is to determine the width of this slice wi in terms of xi star. So what we have across here, we'll call this length a, this horizontal length a. So that wi is equal to, this just equals to, well, this section right here, we know that this is 30. So this is 30, so then we're splitting it in half. So from here to here is 15 meters. And then from here to here is up to a. So wi is equal to 2 times basically 15 plus a. So we have to determine a in terms of xi star. And we could use similar triangles because this length right here, so we know that, again, we know that this is 10 meters. So this is 10 meters. This is the same thing as across like that. And this is going to be 10 meters like that. And the height is 20. So this full height is 20. Oh, let's write this. Let's draw it actually elsewhere. Let's draw this here. So this is 20 meters. So we could use that triangle there. And then, so the ratio of 10 to 20 has to be equal to a up to this point here. And this length, because this full length is from here to here 16. And then from here to here is xi star. So from here to here is just xi star. So what we could write now is similar triangles. Due to similar triangles, the ratio of 10 to 20, because it's the same inside the same triangle, is equal to 10 over 20 meters, and then a over this length here, which is just 16 meters, minus xi star. So this equals to 16 minus xi star. So when we rearrange this, we get a is equal to, this is 1/2, and then multiply this on the other side, 1/2 16 minus xi star. So that's what a equals, and then we could just plug this inside here. So we know that, oh, we don't need to solve this further, we could just plug this inside there. So we have wi is equal to 2 times 15 plus a. So this equals to 30 plus 2a, multiply the 2 just cancel. 30 plus 16 minus xi star. So this equals to 46. So wi is equal to 46 minus xi star. I'll just circle this a bit better. And from here we can easily solve the area AI. So if AI is the area of the ith strip of that thin slice, well, the area is just going to be this multiplied by the delta x, or the height. So we have this width times it by delta x, or the height of each of those subintervals right there. So this equals 2. So wi is 46 minus xi star, and yeah, let's put delta x for there. So that's what our area is. So now if delta x, let's say it's infinitely small, then the pressure pi on the ith strip is almost constant, because, well, if it's really small, the pressure at the top or at the bottom should be pretty much the exact same thing. And what we can write is, well, first of all, recall from my last video that I showed that the pressure is equal to rho, or density right here, times g times d, where this is acceleration due to gravity, and this is the rho, or density of water, and then times depth d, where in our case we have rho, that's 1,000, and again the units all here. We're dealing with SI units. This unit is going to be in pascals. This 1,000 comes from rho is equal to 1,000 kilogram per meters cubed, or the density of water. Let's just say for water. So let's say we have that. I'll just put this in like that. So your 1,000 times by gravity, I'll just put g, and then the depth right here, well, since we had the origin at the top of the surface level, so the depth is just xi star. So that is what our pressure is, and this is our pi. So I'll just write here, recall this is in Pascal units. So again, make sure to watch my introduction video to get a better idea of this. So what we'll have is 100 times g times xi star for the pressure on the dam due to this thin slice across there. Now this pressure is actually, it's a per unit area, so this is the pressure at every single point actually. So this is the pressure at every point. So just to find the overall force. So to find the overall force, we need to multiply, well, it's just the product of the pressure and the area. So basically recall that, well, P is equal to F over A. So that's a force per unit area. So again, our force is going to be equal to the P times A right here. So what we have is force Fi of this thin slice is equal to Pi multiplied by this is the area, so AI, and this AI, this would just equal to, well, 1,000 times it by this is, so Pi is g times xi, and then times it by xi star, then AI, let's scroll where that is, that's over here, 46 minus xi star times by delta x. So that is what our force is for each slice. And now we could just basically add all these forces, and taking the limit as n approaches infinity, what we obtain is the total hydrostatic force on the dam, or the total force due to the water that is static or not moving. So the water is just stationary. So what we have is force. This is again basically applying the integrals to this physics or engineering problem. So this equals to the limit, as we have an infinite, or n goes to infinite number of slices, and then as of the summation I equals to 1 of n sub intervals of Fi. So the total force is the summing of each individual force Fi, which equals to limit as n approaches to infinity. This is going to be I equals 1 up to n, and then we plug in this numbers right here. 1,000 times by g times by xi star, 46 minus xi star times by delta x right here. And now this is a Riemann sum, then this could be, is by definition, you could write it as an integral, equals to integral from 0 to 16, because that's what our meters are. So from 0 meters to 16 meters of, now we have 1,000 times g times this xi star. This is at when we look at an infinitely small delta x, so we get dx. This xi star, it coincides with xi and xi minus 1, so we'll just write x. So the exact same thing. So it's basically, you could learn more about this in my integrals videos in the video links below if you haven't already. So this is going to be 46 minus x, this xi star is just x. Now dx, since we're dealing with infinitely small, or dx, that just means infinitely small delta x. So now we have this, and this g right here, that just equals 2. Let's move this outside as a constant. So 1000 times it by 9.8. This is our g, and this is in meters per second squared. But since everything we're dealing with is SI units, this is going to be in kilograms per meters cubed. This is in meters per second squared. This is meters. So everything is in SI units. What we end up getting is this is going to be in newtons. So unit of newtons, or N. Like that. Again, make sure to watch my earlier video to understand more about newtons. So now what we have is, those are constants, move those out, 0 to 16, multiply these inside. Make it easier, 46x minus x squared dx. Now we just evaluate this. This equals 2, 9.8. This is times by 1000, that's just 9800. And then 46, this is going to be x squared divided by 2. This is going to be x cubed over 3, and that's integral of x squared. This is from 0 to 16, so when we evaluate this, this is 23. 9800, 23, plug in the 16 squared minus 16 cubed over 3, and then when we plug in 0 into these x, that just all cancel out to 0. So we just deal with this right here. So this equals 2 when we plug into the calculator. So yes, when we plug this into the calculator, we get right here, I've put it into this Google calculator, so 9800 times 23 times 16 squared minus 16 cubed divided by 3, and we get this number right here, 4.3. I'll just put this down now. So this equals to roughly 3.33, and again the units are newtons because we dealt with SI units the whole time. Let's get this again. So 443221333.33, 443222133, and this equals 2 right here. Well, actually you could just simplify this further. So this is roughly equal to, write this in exponential notation. So we can write this as 4.43, just round this up to here. And then, so we multiplied by 10 to the power of, well, 1, 2, 3, 4, 5, 6, 7 newtons. And again, this, if you were to evaluate it out, this is just multiply this out, that's just 7 decimal places. So this is just 443, and then 1, 2, 3, 4, 5. So newtons. That's what this part equals to. So that is what our total force is. And another interesting note is if you don't want to just assume that it's newtons, you could just keep the units in every single case. So I'll just put this here. Note, can keep units if you don't want to keep track of it. So what we actually have, let's just go up to here and write all our units, or actually up to this point right here. So we could write as F is equal to, well, it's 1000, which is rho, meters, I mean this is kilogram as density, meters cubed, multiplied by the acceleration of gravity, 9.8 meters per second squared, multiplied by this, where this is this subtraction. Actually, this is the 23 times by 16 squared minus 16 cubed over 3. Yeah, now these units actually, this is an area. I mean, this is a volume right here. Let's just go back up to what we had. So when we were determining that value right here, so this is WI, this is 15 plus A, where those are meters. So this is 15 meters plus A. So this is, let's say, meters plus another meters inside. So what we end up actually having is a width. So 46 meters minus xi, which is also in meters. Scrolling all the way back here. So this is in meters. So if we keep the units, there's a 23 right here. That's just 46 divided by 2. So this is actually 23 meters right here. Times it by 16, where x is again in meters. So 16 squared. I was right, 16 meters squared. Then 16 meters cubed right there. So what we end up having is this meters cubed, and this is a meters times meters squared. So what we end up having, this entire thing is in units of meters cubed. So what we can do is just plug that into our Google calculator. So 1,000 times 1,000 kilograms per meters cubed times it by 9.8 meters per second squared. This is the density. This is the acceleration due to gravity, and then multiplied by 23 times 16 squared minus 16 cubed divided by 3, and then it's put in bracket. It's because we just get meters cubed. I think you could also plug it inside there and you should get it. And it solves this for us and writes it in the exact units, which is newtons, which is pretty amazing. So 4.432213, or 4.43 times 10 to the power of, this is 3 plus 3 plus 1, 7. Let's just test out if this is actually, so if we just put an m like that, 16 m, let's go m, let's see if this solves it. Let's see if this solves it in newtons. Yeah, there you go, newtons. So we didn't even need to do any extra work in determining this is meters cubed. We just plug in the units and then you will solve it, and we get, this is again 4.43 times 10 to the power of 7 newtons, which is pretty amazing with the Google calculator. If you're in engineering or doing any physics and you don't want to deal with the units, just plug it in there and it'll do it by itself. Yeah, and I actually used this when I was in engineering, in civil engineering as well when I did this. So it's very useful, so make sure you understand that Google calculator. Anyways, that's all for today. If you learned from this pretty interesting video and how to apply integration to basically finding the total force on a dam, this is useful for engineering and whatnot. So anyways, like always, you could download these exact notes and link below. And thanks for watching, and stay tuned for another math